result that we get for the TM wave. And for this specific TM wave, we just so we did TE, we did TM, we're looking at the special case of TM, and at this point we can also derive or see some configurations of how the electric field and the magnetic field look like for this specific wave. But meanwhile, we can also remind each other regarding the, wait a second, okay, EY, right here, EY, wait a second. Okay. Okay. Now at this point, since we're discussing about the TEM, I just want to remind a little bit about the writing down all the waves as a function of EZ and HZ. So this is HX, here we have the HY, this is the EX, and here we have the EY. And these four quantities, we said that it is possible for us to write them down as a function of HZ and EZ. So here we have, wait a second, what can we do next? This is 1 over, this is gamma. Okay. This is minus over this third. This is gamma times d over dx, d over dy, d over dx, d over dy of hz. Now, sometimes I try to make them easier to look better, but they might get confusing, discarding my original intention. So this is how we can cluster them. This is the EZ. This is what we get. Then we have minus, plus, minus. Minus 1, plus 1, minus 1, plus 1. Okay. Then we have J omega permittivity. This might really be a challenge now to read them. Now we have the derivative with respect to y and with respect to x. Okay. Here we have with d over dy, d over dx, d over dy, d over dx of Ez and Hz. This is here we have the Ez, and here we have the Hz. Fine. Okay. After some effort, this is what we obtain. And in order to read this, well, let's read, for example, what is Hy from here. Hy is equal to minus 1 over h squared times gamma times the derivative with respect to y of hz, with respect to y of hz, plus J omega permittivity times the derivative with respect to x of Ez. Okay, this is how we want to see it. Now, one reason why we can choose, or why I chose to write it this way, is that when we classify them in a structured way, we can also obtain some intuition about the symmetry of the problem. Okay. So wait a second, there is a mistake on the board. This is plus, this is minus. Okay. So yeah, I mean, here we see kind of the language of the spatter geometry, or the derivative with respect to x and y, which are the only possible ones, because we are writing out of 6 possible components for E and H, which 3 and 3, x, y, z for each one of them. We have 4, which depend as a function of the other 2, Ez and Ez. Now, what can happen, what we can say here is that, in fact, if Hz and, wait a second, Hz and Ez, if these are equal to 0, then imagine for a moment that Ez is equal to Hz is equal to 0. Does this mean, or if they converge to 0, does this mean that the Hx, Hy, Ex, and Ey are this 0? This is a question. An answer would be the following: not if H converges to 0. Okay. Now, these components again, because we see that if this is 0 and this is 0, if we are dividing by h squared, that means that these components here, including the TEM, the transverse electromagnetic wave, and as a reminder, what is TEM? Transverse electromagnetic wave, which is this. Ez is 0, and Hz is 0, but this does not imply, as we said, that these have also to be equal to 0. Now, if h squared, if this one is to 0, what was h squared itself? As a reminder, h squared was written as a gamma squared of TEM, so let me write here a transverse electromagnetic wave, plus k squared. This is equal to 0, okay? So, if this is equal to 0, this means that the gamma here, gamma is equal to the square root of minus k squared, right? So this gamma is equal to jk, so the square root of minus 1 is jk, and here we get j times omega, this is j times omega permittivity. Okay, so this means that the beta, or the gamma itself, so we observe here that the gamma is in fact the beta that we have often seen, and this beta, we have often written this one as omega permittivity times permeability. So it looks like the propagation constant in a waveguide over the TEM wave, so this TEM wave, this is similar to the propagation of waves in vacuum. Okay. But not only waves, of plane waves. So we've seen the plane waves so far in the previous chapters. And what was the first thing that we did? So whenever we were analyzing the motion of a specific wave, we used to look at the frequency, at these. We say the first thing, what is the frequency? Okay. After the frequency, we should find omega. The second thing we asked was, what is the permeability? Often it was equal to mu0 because we were dealing mostly with non-magnetic material. The third thing that we were looking for, what is the ER, the relative permeability. Once we get these three values, we say, okay, we can easily find the beta, which is equal to omega square root of mu permittivity phi. This is what we used to find for in the propagation of plane waves. Now here we observe the TEM wave. It propagates with the same features or the same propagation factors as a plane wave would move in vacuum. Okay, we have here, and the equations here for the EZ. Let's have a look for a moment. This is C4 times cosine. Yeah. And for the TEM wave, let's write here in black. This is equal to C4 e to the power minus gamma 7. Okay, so let's assume n is 0, because at this n equal to 0, this is what we get. And then if we insert n0, we get only the EX. EX at that time will be equal to gamma divided by j omega. Okay, so this cosine will go. So this cosine will go, and allow me to write. This becomes a little. So in black, you can find out the fields for n equal to 0. We have here gamma C4 over j omega permittivity. Cosine is gone. E to the power minus gamma z. This is all that we are going to see for the TEM wave, so here and here. So these two quantities will be the non-zero quantities, because the EZ would be equal to 0, again in black. This is the TEM. And this really looks like a transverse plane wave, because in the plane wave we used to simply have EX and HY, and we could obtain the EX cross product with HY. This is the KZ, okay, which would be the propagation along one of the directions. Okay. Now, okay. Now we can. Okay, we did this one. We did this. Okay. Well, now what I want to talk about is that let me see. We want to make to EXHY. Let's see here. Now to construct the next argument. Okay, maybe the next thing that I wanted to discuss is in fact how the impedance of a waveguide works. Okay, but the impedance of a waveguide including only the TEM mode. Okay, so I believe we can do that. Just that this will include Here we go. Okay, we have to do it. It might take us some short instances. So let's take this away. We just have a look at these expressions by also trying to see the symmetry of the problem. And let me erase this because this is also clear why we have the TEM mode from the TM. And I just want to write very fast these expressions. So from the curl of E, we have gamma EY, this is equal to minus omega mu hx. Then we have minus gamma EX minus the derivative with respect to x of Ez. This is equal to minus j omega mu hy. And we have the derivative of Ey with respect to x is equal to minus j omega mu hz. Here we have the three equations. These are the equations that I always try to refer to. Okay. So many derivations that we have done so far, even into these two sessions. If you have any question, you always go back to your notes. You look at these three equations. That is what I was reading. Now, similarly, let's write here gamma hy. This is equal to j omega permittivity ex. So in fact, even this pair of equations, we can simply interchange hy with ey. We make j omega, we make minus j omega. We substitute the mu with the permittivity, and hx becomes ex. Okay, so there is a strong similarity between these two curl operations of the two Maxwell's equations, and which in fact, if we have 6 major equations over which we are considering the solution, we can even write them down, simplify them into 3. Let's continue here. This is minus gamma ehx. Again, as we're writing this, you can always keep an eye in here and see how similar they are. Minus gamma hx minus the derivative with respect to x of the hz. This is equal to j omega permittivity ey. Again, how much different are they? The j becomes minus j, the permittivity is permeability, ey is hy. Okay, they are completely similar. So here we have the final expression, which is the derivative of with respect to x of hy. This is equal to j omega permittivity Ez. Okay, good. So let's have a look at these equations, and then let's try to look at the following expressions. So here, if we look at equation 1, let's try, which is this. So let this one be 1, 2, 3, 4, 5, and 6. Okay, from the first equation, it looks like we have ey, we have this expression. But the moment that ey is equal to 0, what does this imply? If ey is 0, we get that hx is 0, right? Based on the first equation. Now, this means that overall, we have that if hz is equal to ey is equal to hx equal to 0, these are the only 0 terms, and we get the rest 3 components, which will be hy, ex, and ez. They are all different from 0. So these values being non-zero, they would sustain the wave in the system, or in the waveguide. Let's say it in the waveguide. Now, with these equations here, we can then add that from the second equation, or wait a second before we move into this. We should not also forget this part here, which is for the TEM mode. But let's have a look at equation 2. But now let's consider the TEM mode. What could happen? Now, equation 2 is here, and EZ equal to 0. What this implies is the relationship, a direct relationship between EX and HY. And we can write that EX divided by HY, this is equal to J omega mu over gamma for TEM. Okay, so J omega mu times this. But now we can remind each other what is the gamma. So if we have a look at this gamma here that we found for TEM, we can, this is the expression is done. Okay, so let's close this one here. But then this is a direct consequence of this expression, assuming that this is going to be 0 for TEM. And this is here, we have J omega mu. Gamma is J omega mu permittivity. J omega from here, mu times permittivity. So again, allow me to write this here. This is EX over HY. This is equal to J omega, that will cancel out. And the permeability divided by the square root of permeability is equal to this. Where have we seen this expression before? So this is the intrinsic impedance of a wave in an unbound region, okay, in a region which is unbound. And what is important here, which is also very relevant to the waveguides, is that this ratio, which is equal, so we have seen this one a lot, right? So we were given the amplitude of an electric field, we divide by the intrinsic impedance, we find the magnitude of the H, that's fine. But another important element here is that this intrinsic impedance is not a function of the frequency, okay? So this is not a function of the omega, or you can write this one as F, the frequency, right? So this is something very important. In waveguides, the propagation is frequency dependent, but apparently for TEM, based on all of these equations, which we elegantly try to write it down, this is what we get. Now, this is from the second equation. From the fourth equation, we can also, which is, wait a second, from the fourth equation, or maybe we can use this, the fifth, gamma HY plus the derivative of HZ with respect to Y is equal to J omega EX, yes, okay.
Professor, can you do that?
Yeah, so we are almost done, so we can even come to an end.
Okay.
But what I want to make clear is that in waveguides, so apparently, let's just, this derivation that we saw here, it was essential to understand that the ratio between these two respective fields, E and H, their amplitudes, they are related by this. So we are really into this domain. So TEM in a waveguide is similar to the propagation of waves in vacuum or in unbounded regions. In unbounded regions, and why is this the case? Because in a waveguide, but then we're going to add it here, in a waveguide, the propagation depends on the frequency. So for next time, I would strongly suggest you to read from the book regarding the cutoff frequency. Okay, so in a waveguide, how can we think about it? Of it? Maybe the best way is to think this one as a parallelogram, which is like a tunnel, where we can assume this has a parameter A, okay, this has another parameter B, and we want the wave to propagate, but how does the propagation depend on the frequency? Apparently this doesn't. In the general case it does. So we have a cutoff frequency. We consider this one frequency C, a critical frequency or cutoff. But the moment we have a cutoff frequency, we should have also a cutoff wavelength. Okay. So have a look in the book or in the notes, and maybe you might be ready when we meet the next time in the future. Okay. Any question? If you have no more questions, we can stop also for today.